first important property is equivariance. So equivariance basically says that if you want the MLE of some function of theta, then all you have to do is so then the MLE is just that function applied to the MLE of theta. That didn't quite come out so cleanly, but here all I'm saying is that if G is a function, then G of theta hat is the MLE of G theta. So let's take a look at an example. So say again that X is Bernoulli theta, and we wanted to find an MLE of the variance of X, which is theta times 1 minus theta. So this, so this is G of theta here, right? And so according to the equivariance property, the MLE of theta 1 minus theta will just be this thing. So theta hat times 1 minus theta hat. It's that easy. The reason that it's true is that all that we're doing here is we're basically reparametrizing. So in this situation, let's say that so our likelihood function, if our data is X is 1, so that's this line here, and so that's this diagonal line here, and we're looking for theta values between 0 and 1. Now, G of theta takes values between 0 and 1 over 4. So as theta runs between 0 and 1, G of theta, let's call that phi, runs between 0 and 1/4. So we now have, so we've now reparametrized our parameter to run from 0 to 1/4 instead of from 0 to 1. And now so we don't need G to be 1 to 1. It could be, for example, 2 to 1, but then we just have to, when we define our likelihood function, now we just need to say which value we need to take. So for example, the likelihood of zero, well, what should that be? So so zero here, that maps to 0 and 1. Because 0 and 1, G of 0 and G of 1 are both 0. So going backwards, 0 maps to 0 or 1, and what we're going to do is we're just going to take whichever value of f is larger. So clearly, 1 f of 1 is larger. So basically, we'll go like this, and so this will be our this will be our likelihood value. So we're defining, for example, the likelihood of phi is 0. It's the maximum of the likelihood where theta is 0 or theta is 1. in other words, the max of 0 and 1, which is 1. So this will define for us right. So now for every value between 0 and 1/4, we get a unique value of f, and we're just looking for the value of phi that is that gives us the largest value of f, right? The largest likelihood. So right. So phi hat is just going to be theta hat 1 minus theta hat, which is x times 1 minus x. And so x is 1 in this case. So these go the opposite way. So this is 1 times 0, which is just 0. So under our new parameterization, the MLE is 0 when x is 1. Okay, so equivariance is an important property. Consistency we've seen before. That's true for MOM estimates as well. So it just means that our estimator converges in probability to the parameter, except that it's not always going to be consistent. You need certain requirements about your about your setup. So your data points need to be identically distributed. The parameter theta needs to be an interior point in your parameter space. Your log likelihood function needs to be differentiable and have a unique solution when you set the derivative equal to 0. So we're going to, for the most part, assume these things are true in the examples that we look at. Okie doke. So now we are going to go to section 8.53, which is about assigning a confidence interval to our parameters, but we need to learn about chi-square distribution and the t distribution. So you should have met this in your probability class. I don't really have anything to say about chi-squared, I don't think. This is the distribution here. I think, so an interesting thing is that, right, so an interesting thing is 1 over sigma squared sum from 1 to n of xi minus mu squared. That is chi-squared with n degrees of freedom. But if instead of mu you substitute x bar, it's now chi-squared with n minus 1 degrees of freedom. The proof of that requires some probability machinery that we're not going to get into. I'll just say intuitively, the reason it goes down to n minus 1 is that there's a dependence now between the whereas before the xi minus mu were n independent normal random variables. Now the xi minus x bar has a linear relationship. Basically, the sum of them is 0, and that means that we lose 1 degree of freedom. So 1 over sigma squared sum of xi minus x bar squared, which if you follow the definition of what the sample variance is just n minus 1 over sigma squared times the sample variance. That is chi squared n minus 1. So that's an important result that we're going to assume. And so the upshot is that s squared is really just a multiple of a chi-squared n minus 1. The t distribution is very famous. It consists of a standard normal divided by a chi-squared, and the main thing is that when you normalize, so say that you have x1 to xn IID normal, but now sigma isn't known, then when you normalize, you're going to normalize with the sample standard deviation, which now, instead of giving you the standard normal, is going to be the t distribution, because if you rewrite it, you can see that x bar minus mu over s over square root of n is exactly in this form. So it's a tn minus 1, which looks like the normal distribution. Okay, so almost there. Now, the last part of class, we wrote down like what a 95% CI for mu and sigma squared look like in sort of an exact calculation. And this is something that you can work out exactly now that we know chi-squared and the t distribution. So we start off and just follow the book here in how they calculate the MLE for mu and sigma squared. For mu, it's the sample mean, and for sigma squared, it's 1 over n sum xi minus x bar squared. Just a note here that in the book calculates sigma, so the estimator for sigma, but we want the estimator for sigma squared. But just by the equivariance property, we know that the estimator for sigma squared is just the estimator for sigma quantity squared. And also just note that we can see that the MLE estimator for sigma squared is biased. It's not s squared. Okay, I'm going to go through this quickly because this is similar to what we did in the first lecture. So you define alpha between 0 and 1. You look at the sampling distribution for x bar. You normalize it, but now we don't know what sigma is, so normalize means x minus mu over s over square root of n, which is a t n minus 1 degrees of freedom distribution. So the probability that that is between the alpha over 2 quantile and the 1 minus alpha over 2 quantile is having probability 1 minus alpha. And we basically just solve here for mu, just like we had done in the first lecture. So this is the formula for a 1 minus alpha 100% CI for mu. And now we're going to do a similar thing for sigma squared using the chi-square distribution. But now sort of our normalized distribution, it's not going to be oh yeah, it's going to, so our test statistic, our estimator is is sigma squared, is our MLE estimator. So this, but we're going to multiply it by n over sigma